Thank you, Andrew, and thank you very much. So I would like to talk about some new things that have happened and trying to understand deep learning, and in particular to the specific ways that we are learning from deep learning, the new phenomena that we are trying to understand based on the practice of deep learning. I actually kind of find it very useful to think about it in terms of the lessons of deep learning, is that by looking at the practice, we can understand, try to see what is it that we need to understand and how can we approach. I'll talk about two lessons today, really only lesson one is about statistics, what we need to understand about statistics from the practice of deep learning. Very brief, I mentioned the lesson two, optimization. And the common theme of what we're observing, and at least what out, will be this idea of overparameterization and interpolation. So let me start beginning, and I will just very, very briefly. What do we do in machine learning, right? We have input data, xi, yi, and we would like to, based on this data, predict data that we haven't seen. So we would like to construct a function from the feature space to the output space, maybe just -1 and 1 to be really simple class problem, that best generalizes. And what does generalization mean? Well, under the simple assumption when data is chosen IID, you can simply say that the best statistical predictor is the function which minimizes the loss of unseen data. Now, of course, to minimize the loss of unseen data, we have to have access to the unseen data, which is by definition is not possible, right? Since we haven't before. So what do we do in practice? Well, in practice, more theory, we consider the empirical risk minimization. What is empirical risk minimization? We choose a family of function, and we try to choose a function from the family which minimizes the loss on the training data. So instead of unseen data, we take the training data, which is the data we have seen. And instead of choosing all functions in the world, we choose functions from some family of functions, like neural networks, for example, of certain architecture. So you can see the goal of machine learning and the goal of empirical risk minimization are very similar, but not quite the same. Importantly, there are important differences. Now, let me very briefly describe the classical view. So what I'm going to do is I would like to describe the classical view of this, and then I would like to show why this classical view in some sense is unsatisfactory. And then I point out to this kind of new ideas which will help to explain what we observe. So the classical view of this, and a lot of it is due to Wapnick, it's described very nicely in his book, Statistical Learning Theory, is that the theory of induction, as he calls it, is based on the uniform law of large numbers, that's one, and effective methods of inference must include capacity control. So to unpack this, what is uniform law of large numbers? Uniform law of large number simply means that for my class of functions H, empirical laws for any f in this class of functions approximate the expected loss of f. That's exactly a uniform law of large numbers. That's one. Now, what is capacity control? Capacity control means that H must contain functions that approximate f star. If f doesn't have functions which approximate f star, this is kind of a doomed enterprise, right? If in your class of functions there are no good functions, then there is no point doing this at all. Now, it is easy to see that if you have 1 and 2 together, then the loss of the empirical optimal and the loss of the true optimal will be similar. That's kind of the main result of this line of investigation. To connect the loss of f star rm of f star. And of course, if we can find a function like that, f star rm is good, because it's close to the best. Well, what about uniform laws of large number? To unpack this a little bit more, uniform laws of large numbers work like this. You have inequality, which you may call Wysiwyk. What you see is what you get. So This inequality is of the following form. On the left, you have the expected risk. This is the risk of unseen data. This is what you get. On the right, you have the empirical risk. This is what you see, right? This is a loss on the data that you have. And the inequality works as following. It says that what you get is bounded by what you see, plus some sort of model complexity term, which is either a model or function complexity. There are many, many versions of this, hundreds probably. So that is uniform loss of large numbers. Now, what about capacity control? Capacity control, according to Vapnik, works as following. You increase the capacity of your function space. And when you increase the capacity, of course, you can fit the data better because you have more functions to fit the data. So empirical loss goes down, empirical risk decreases. But the second term, this model complexity term increases because the model complexity goes up. So one term decreases, the other term increases. And the idea is to find the point where there is kind of the optimal, the bottom of this U-shaped curve, by making them roughly equal. That is the goal, to find this bottom of the U. The way it's done in practice is usually something like that. This is kind of a heuristical reinterpretation. This is from Elements of Statistical Learning by Hasty, Shirani, Friedman. As you increase model complexity, the training loss decreases, the test loss decreases, and then goes up again. On the left, you have underfitting. On the right, you have overfitting. And the goal is to find the sweet spot, the bottom of the U. And a kind of corollary to this is that the model with zero training error will generalize poorly. But the bottom, the model with zero training error is on the right end of this diagram. We call it interpolation just for future use. Interpolation mathematically, it fits the data exactly. But so very recently, actually the evidence for this is much older than that, but I think recently it became much more clear that this story has some problems. And there's kind of a very nice example from Zhang et al. They did training of a neural network on CFAR10. They get 100% train accuracy. And you can see that even though train accuracy is 100%, test accuracy is still very good. It's almost 90%. So you don't actually see much overfitting. Well, on its own, this is not quite enough because you may still say, well, 90%, maybe it's still all right. You cannot quite say, but this is that there is no overfitting, but this is very suggestive of it. And to somehow see it more exactly, we did the following experiment. This is joint work with Siwan, my student Siwan Ma and Sumik Vandal. What we did, we randomized the labels for, so this is feminist, it's a 10 class 100-digit data set. We randomized the labels for it. So on the x-axis, you have the level of randomization of the labels. So there are 10 possible classes, it's 100 digits, right? 1, 2, 3, 4, and so on. For say 10, 20, 30, and so on % of the training labels, we just assign a random. Okay, and we do the same way for test and train. Now, this becomes a very noisy data set after you randomize so many of data points. And you can see that the green line here, let me just ignore the rest of it. The green line here is the base optimal. You cannot, if 10% of your random of your data are random, you cannot do much better than 10%. That's just not possible. They're random, right? You cannot predict them. So the green line is the best optimal. It's theoretically better than the green one. 90% is random because if you just choose them at random, you will have 90% error rate. Now, what you see is that this red line, which is Laplace kernel machine, it doesn't matter exactly what it is, but neural networks behave very similarly. The purple line is neural network. And you can see, even for very high noise levels, it's not that different from the green line, even for 70 or 80%. Much better than random. Now, what is this training machine? What is this Laplace kernel machine? It's actually trained to have zero training loss, not just accuracy, actual loss, it's square loss. So it fits the data exactly. It exactly interpolates mathematically up to numerical accuracy. And even though it fits this noisy data, it still does fine. right? No problem. I mean, it's slightly worse than the optimal, but it's still much better than random guess. So what is the implication? The implication is that this type of behavior is very difficult to explain from the point of view of usual generalization bounds. Why? Because this loss is not the training loss. That means that test loss must be directly bounded by the model complexity. But this is very problematic. Why? Because, well, if you look at this, if you look at the level of, say, 70% label noise, you will see that bound cannot be built, it would be wrong. It cannot be above 90% because it would be trivial. So if you want to have a bound which is non-trivial and hopefully correct, it has to be between 0.9 and 0.7. And presumably as n goes to infinity, that should hold. Now the problem is that first this constant has to be exact, and we don't really have bounds, well, unless some very, very special cases, we don't have bounds with exact constants. Usually the log factors are all sorts of other things there. Second, how would quantity under the square root even know what the correct level is? Because the correct level, it has to do something with the Bayes risk, right? It doesn't have this detailed knowledge about the problem. And classically, this is handled by the fact that you have empirical loss. Empirical loss has the knowledge about the Bayes risk, but in this case, we don't have empirical loss. So that's kind of what you can say, is that first, there are two things. First, empirical finding is the goal optimization. Interpolation unexpectedly aligns with goal of machine learning, minimizing the loss. And this is unexpected because I don't think, like, somehow fitting noisy data exactly seems like a wrong thing from a statistical intuition, but yet it seems just fine. Even very noisy data, like with 70% noise. And clearly the bounds that we have cannot account for generalization on the interpolation when data are noisy. Now, so that may be like this kind of the first lesson of deep learning. And it's a lesson of deep learning, but it doesn't just apply to deep learning. In fact, what I showed you was a kernel machine. It wasn't deep learning method at all. But similar empirical observations, of course, hold for that. If a theory of induction for learning cannot be based on uniform last numbers in capacity control, we need a different paradigm. We need a different set of techniques. And I'm going to, we don't have a complete theory for this yet, but we have at least some ideas of where it should go. So that's what I'm going to talk about next. Okay, now let me point out that there is one classifier for which we know it interpolates and it does okay. And it's the simplest one. It's kind of funny, you know, like nowadays, I think when you ask people, okay, what's the simplest classifier? And, you know, people think about neural networks. No, actually, the simplest classifier is one nearest neighbor, right? It's just prototype learning. You have your data, you have a new point, you just find the closest one, right? That's, I would say this is the simplest. And the interesting thing, it's an interpolating classifier because you, for each example, right, you assign the same label to it. So it's an interpolating classifier, it's really simple, and it actually has a theoretical guarantee. It's twice the Bayes risk. It's a classical result due to Haber and Hart. Now, of course, it's not optimal and it's very far from optimal because instead of the optimal, right, you get twice the optimal. So instead of 10% error, you'll have 20%. Pretty far. It turns out that there is a way to actually have something like nearest neighbors, which is optimal. And this is related to something called Shepard's interpolation. It's some sort of interpolating nearest neighbor scheme. Yeah, I should point out this is joint work with Daniel Su and Partha Mitra, the follow-up on statistical optimality with Sasha Raklin and Sasha Tsibakov. And basically the idea is if you take a weighted nearest neighbor scheme, and the weight is such that as you approach a point, it goes to infinity. So it's like inverse distance weight. Then this becomes an interpolating classifier, and you can prove that it is optimal in the sense that it converges to the optimal in the limit of infinite data, and in fact, even the rate is optimal. So it's fairly strong sense optimal for regression and classification. for the minimax rated for classification. I'm sorry, for regression. Okay, I see there was a question.
I think we can hold it for the end if you're fine with that.
Oh, that's yeah. Then what do we have? If you look at this blue curve, so what do I have on this picture, just to give you an idea what is happening? My data, which are these little circles, are sampled from the blue line plus noise. So it's a linear model, right? Linear plus noise. And of course, the blue line is the best possible. If you know a priori what it is, you should do blue line. What does this method give? It gives you this red line. And the red line goes through every data point. So you can say, okay, this is crazy. I'm fitting all this noise exactly. But actually, if you look carefully at it, you see that it's not really a big deal, because even though at every data point you are far from the blue line, on average on this line, you're actually pretty close. So this is kind of a remarkable thing, right? You're at every data point, you're really doing badly, but between those data points, you're doing okay. And this is kind of a visualization of the theorem. You can prove that this is optimal in the limit. It's the data because it's infinity. So at least it's not optimal in some sense, and also interpolated. But of course, that's not what we do in practice, right? This is not the kind of method which is commonly used in machine learning. What people use? Well, people use, nowadays a lot of it is neural networks. So what about neural networks? And the neural networks, I think, have this remarkable property that it's very easy to decouple the number of data points from the complexity of the model, right? Complexity of the model has nothing to do. It's a purely architectural choice. You put, okay, I have 1 million parameters or 1,000 hidden units or something like that. It has nothing to do with the number of data points. And what you realize is that when you increase complexity beyond this point of interpolation, beyond where you have enough to fit the data, something really interesting happens. So up to the point of interpolation, you are tracing this classical U curve. But you're doing very badly at the point of interpolation, this kind of interpolation peak. But the amazing thing is that once you go beyond the point of interpolation, this drops again, and often drops indefinitely at all asymptotes to infinity, to something. No, not to zero, of course, it cannot, but to some relatively good number. And frequently, but not always, this kind of infinite point is better than the bottom of the U. So we call this double descent, and we really did quite a few experiments for random forest, for neural networks, for boosting, and for other things. It seems to be a very consistent, robust phenomenon. And I should point out that other people also observed this effect, and including Andrew, and in particular, Advani Sachs they observed it for linear models, and Spiegler et al. For some certain types of neural networks. And so it does seem to be fairly general, quite general actually, at least as general as a U-curve, I would argue. Now, I would like to, I don't have a lot of time, so what I would like to do, I would like to maybe just give an example of what it looks like in one dimension so you can kind of visualize it. So imagine this, I have one-dimensional data, this red point, and I'm building a very simple one hidden layer neural network. I don't want to describe it since I don't have time. So with 3 neurons, you get kind of fit like this piecewise. They're always piecewise linear because they're ReLUs. With 30 neurons, and this is reasonable fit, right? This is like a good parametric fit. With 30 neurons, I get classical overfitting, right? It goes crazy, which is you would expect. But the amazing thing with 3,000 units, right, it looks nice again. And in fact, you cannot even tell that it's piecewise linear. This is actually a piecewise linear function, but because there are so many linear pieces, it looks smooth. And of course, if you do 3 million, you wouldn't be able to tell the difference between 3,000 and 3 million. It looks essentially the same. So this is a true non-parametric model in a sense. Even though it's parametric, it's kind of not parametric because 3,000 and 3 million makes no difference. Okay. Now, I should say that we now have a bunch of analysis in various settings, and in the last maybe year or two, basically showing that this really does happen, at least for linear regression in certain settings, we can prove it and we can analyze it precisely. And there is a lot of evidence that for neural networks, this is really what's happening. This is not proved for general neural networks, but there is, I think, prevalence of evidence for that. Now, I would like to say that this, in a sense, you can view it as a different framework for modern machine learning. By modern machine learning, of course, I don't mean technically just modern machine learning, but the kind of over-parameterized learning that is used now. It goes, you have to look at history, it goes, of course, back. And basically, it's a principle of Occam's razor, right? What is Occam's razor? Occam's razor is, you choose the simplest explanation which fits your data. And in this case, you can kind of say, fitting the data is just interpolating, right? That's perfect. That's exactly fitting your data. And what is the simplest? Well, the simplest is some sort of inductive bias. And usually in these settings, this is some form of smoothness, and the smoothness can take different forms. It can be explicit in terms of minimum functional norm. And this is the way it's done for kernel machine. It can be implicit through optimization. Or it can be by some sort of averaging, when you take some trees and you average them, and the resulting average tree is smoother. It's a kind of form of banking. The resulting tree is smoother than any of the individual tree because you're averaging them. And I think there is something interesting for kernel machines for those who are familiar with that, because all the things can be shown to coincide, which is, I think, really remarkable. Okay, so I think I'm going slightly over time, but I think I'll talk about, let me kind of summarize what I said, and then I'll say like maybe 1 or 2 minutes on optimization. The landscape of generalization, as we understand it now, on the left, you have this classical analysis where what you see is what you get bounds applied. On the right, you have this modern interpolation regime based on deductive biases, and we're now seeing first analysis of this. And I think one remarkable aspect of this is that overfitting now, as we understand, is not directly related to just fitting the data exactly. It's actually a band of parameters in this kind of landscape. So that's, I think, one very specific different view that we need to take from this one specific lesson. What is overfitting? Overfitting is not what we used to think it was. Okay, now I'm going to just very briefly say something about optimization, and it's a separate discussion, but I do want to point out that there are lessons for optimization as well, and I think those lessons are also quite important. What is classical optimization? Classical optimization is that non-convexity is bad. There are many local minima, no general global optimization technique. And usually the picture is drawn as something like this, right? You have a bunch of local minima and you don't know how to choose one. This picture is deeply misleading for over-parameterized system because it actually kind of implies local convexity at each of the minima. And also it implies that somehow this minimum are separate. The picture we should really think about is this one, and this is from our work with Leo and Libenjo, my students. This is the landscape. That the landscape, really, you have a family of global minima which form a band. And in some sense, this is quite different because you can see this landscape actually not convex. It's not convex in any neighborhood of any point. And you can see it, well, I don't have time to describe, but you can see it. If it were convex anywhere, locally it would have to be a line, but it's never a line. There is curvature to this curve at the bottom. So we really cannot think of convexity, even locally. It really has to be essentially non-convex. it turns out that we have a set due to Pollack and Lajaszewicz originally. That's three. There is Pollack-Lajaszewicz inequality, which implies convergence of gradient descent and convergence of local depth. So we do have tools, but these are not the same tools as convexity. So we have to get away from that. Okay, so let me summarize. On the left, we have this classical model. Careful parameter selection is required to find this bottom of the U. Many non-global minima, and there is local convexity as the solution. In the modern model, we have this good generalization from inductive bias, and it's not sensitive to the number of parameters, not so much, right? If we move left or right on this curve a little bit, it doesn't make a huge difference. So that's, I think, what we observe in practice. Basically, taking a very large system often just works, and you don't really care how large as you basically can fit into your memory. So, and all minima are actually global minima. So finally, let me finish with, it's a neuroscience conference. I would like to say at least something conjectural about neuroscience. And that I think we're now we're seeing some new mechanisms, but we're starting to get some new understanding in machine learning of these mechanisms, both for statistical optimization. And the question is, well, can this serve as a basis for biological learning? And I think, I'm not an expert in neuroscience, and so take this as a pure conjecture, please. But I think this makes sense because this mechanism somehow are very robust, right? We don't care how many parameters we have so much. We don't, it's just some local update rules. They just seem like a very reasonable mechanism for a biological system to have. And, you look at the human brain, well, there are tons of neurons there, right? There's something like 100 billion neurons and 10 to the 14 synapses, right? So why can't it? I'm not saying this is actually what happens, but at least on the surface, it wouldn't be absurd to say that maybe something like that is happening. We have enough somehow, we would do some sort of updates, some Hebbian rule or something, I don't know. And maybe some of this mechanism can actually work biologically. So maybe I'll stop here.
Thank you. Fascinating talk. So I'll pose a few questions from our audience. The first is from Tatiana Engel. She asks, if we fit noise in the data exactly, would this lead to good generalization performance, but bad behavior on adversarial examples? So I guess, is there a relationship to adversarial robustness in your view?
Absolutely, yeah. That's an excellent question. In fact, we discussed it in this, let me just go very quickly. We discussed it in that paper, in fact, specifically. It provides a mechanism for adversarial examples. Like if you look at the graph, you see that it will have tons of adversarial examples, right? And what you can show is that if you fit your data exactly, as long as the labels are not deterministic, so as long as there is any noise in the labels, you will always have adversarial examples. And I don't think this is the only mechanism by which adversarial examples arise, but it is certainly very, very consistent as well, right? That for architectures for different things, you get adversarial examples.
All right, so maybe I'll smush the last two together so you can answer them in one go. I think that the broad question is, you've shown that models can generalize well, but they may not recover the underlying low-dimensional model that generated the data. So is that a reason we have to be careful in even comparing these models or using them in neuroscience? Because you could get a system that fits the data but doesn't reflect the generative mechanism.
Absolutely, yeah. I think this is an important distinction. Somehow, when you're doing, I think there is maybe this is a different paradigm almost, because you see in science, right, you want to identify one thing or a small number of things, and you say, these are my controls, right? Like physical laws, they don't depend on a lot of things, right? Like the gravitation force between two objects is inverse proportional to the square of the distance. It's simple. So in science and neuroscience and other things, we would like to identify a few parameters and say these are the important things. I don't think these models can do that. They really don't identify that. So if you know the mechanism, if you know something about the mechanism, I think you still have to use that mechanism. What they are saying is that in the lack of knowledge or in the very weak knowledge about the things, we can throw a bunch of features which only vaguely, weakly correlate with what is predicted. And that's okay, that's good for prediction, good enough. But I don't think it has explained, so that's why I'm a little bit skeptical of the attempt to extract the actual laws from neural networks, because I think they have strong predictive power. Doesn't mean that they encode the actual laws, the actual scientific knowledge in them. So really, I think we have to separate.
All right.
I feel there are separate modes of inquiry.
Great, yes. And there are more follow-up questions on Slack if you have the chance to go look at those. So thank you very much. I think we have to move on to the next speaker.
Thank you.